In this video, we derived the Nernst equation for electrochemical reactions. Alright, this work is going to build up on the relationship that we have found out between the standard cell potential and the standard Gibbs energy. Okay, remember that that expression was as follows. For an electrochemical reaction, the standard change in Gibbs energy, or the change in Gibbs energy at the standard state, is equal to minus the number of moles of electrons that are being transferred in the electrochemical reaction times Faraday's constant times the cell potential under standard conditions. And remember that the cell potential under standard conditions is simply the balance of the cell potentials of, or the half cell potentials of the cathode and the anode. These are standard potentials as well. And remember that these potentials are given in table as reduction potentials. Right, so this is nice because we can calculate whether the reaction will be spontaneous or not under standard conditions, but it's also limiting because we're constrained to standard conditions, and that would mean that in your electrochemical cell, if you have concentrations, solutes, those need to be at 1 molar concentration. And if you have gases, then those would need to be at 1 atmosphere of pressure. But of course, most batteries don't work under those conditions of concentration of pressure. They have other concentrations. The question is, well, can we predict spontaneity and actually the amount of work that you can get out of those batteries under any conditions, not at the standard state, but under any conditions? And the answer is yes, and that's where the Nernst equation is going to provide. Now, to see how the Nernst equation develops, we need to remember that this tends to be very similar to something that we did when we were looking at the Gibbs energy. And that is the fact that if you want to calculate, for example, the Gibbs energy in a reaction, okay, under any conditions, that simply was given by the Gibbs energy of the reaction at the standard state plus a correction, which was RT natural log of the reaction quotient. Okay, so taking a cue from this, we can then try to see how this would work now when we involve cell potentials, right? So notice that if we're working not at the standard state but under any conditions, right, the Gibbs energy then for that electrochemical reaction would be NF times the potential of the cell under those conditions, right? That is that follows naturally from the expression that we have right there. Okay, so now what we actually have is the Gibbs energy under any conditions and the Gibbs energy under standard conditions. We can actually see that they should follow this relationship, and that is what's going to lead to the Nernst equation. All right, so we take that expression, and now we're going to replace it by minus NF E cell, and then here we have the Gibbs energy at the standard state, which we also have. It's minus NF E cell at the standard state, and then plus RT natural log of Q. Again, the only thing that we've done is taken the universal expression for how the Gibbs energy of a reaction changes with concentration, and simply replace the terms with what we have seen in electrochemistry that depends on the cell potentials. Okay, so this is our expression. Now, we're going to consolidate this a little bit by dividing everything by minus NF, right? So what we have here is this E cell, which will be the potential of the cell under any conditions that we wish, okay, is equal to the cell potential under standard state conditions, and then that is going to be minus RT over NF natural log of the reaction quotient. Okay, so this is actually the Nernst equation. Now there's a different form of the Nernst equation that we will be using in problems, which simply takes all of these numbers and considers that R is going to be 8.31 joules per mole Kelvin, the temperature is going to be 298 Kelvin, so that will be room temperature. This is a constant, and then there's also a change in the natural log, in the logarithm from the natural to the base 10 logarithm. Okay, so that expression is going to look like this. E cell is going to be E cell at the standard state, which we can calculate very easily, minus 0.0591 over n base 10 log of Q. All right, so if you put here the number of electrons transferred in that reaction, then you will get this cell potential in volts. Okay? All right, so this is what we're going to be using, and again, it only works for 298 Kelvin, but that's fine because normally we're operating under those conditions. Okay, so this is a very nice expression because again, it allows you to predict what the potential of the cell is going to be and whether the reaction will be spontaneous or not, if you know what the cell potential is under standard conditions. And again, that's easy to calculate because we have tables in which we have all of the more interesting reduction half cell reactions, and we can calculate the standard cell potential under those conditions. So we have this number, and then you just balance the reaction to figure out what the number of electrons transfer is, calculate the reaction quotient, which is something that is also straightforward to calculate, and then again you will be able to predict what is the potential of your cell under those specific conditions and whether the reaction will be spontaneous or not. Okay, so in next videos we're going to see examples for how that equation kind of crystallizes and can be used to our advantage. Before we go to the next video though, I'm going to show you here something that is going to be important, and that is what happens when you reach equilibrium. Okay, so the idea is that you might have a cell that is producing some electromotive force, right? So you have a positive potential, you let the reaction go by, and then as the electrons are transferred, the concentrations of reagents and products are changing, and eventually you will reach equilibrium, and then you won't have any longer an electromotive force. That's when your battery is fully discharged, right? So the question is, well, what happens then? Well, notice that at equilibrium, what is going to happen is that this is zero, and that means that you don't have any potential anymore. So at equilibrium, E cell is zero, no electromotive force. You have exhausted your battery. And then what happens also is that your reaction quotient, once you reach equilibrium, becomes the equilibrium constant. Okay, so then your Nernst expression turns into zero, is equal to the potential of the cell under standard conditions minus 0.0591 over n based on logarithm of the equilibrium constant. And what that tells you is that there is a direct relationship between the equilibrium constant of your electrochemical reaction and the cell potential under standard conditions. And again, that's beautiful because now you can measure equilibrium constants from knowledge of the standard cell potential. But the standard cell potential is trivial to calculate, right? If you know what the half reactions are in the cathode and in the anode, these potentials are available in tables, which means that the calculation of the standard cell potential is straightforward, and then you can figure out what the value of the equilibrium constant is. Okay, just to wrap this up, we can say that the relationship between the cell potential under standard conditions and the equilibrium constant is equal to 0.0591 over n based on logarithm of the equilibrium constant. And again, that expression here is constrained to room temperature, 298 Kelvin. Right, so in this video we have seen how to calculate the spontaneity and the cell potential of an electrochemical cell, of a battery, under any concentrations or pressures of reagents and products that we wish. Okay, that is called the Nernst equation, and again, that allows you to predict spontaneity. Subcase of the Nernst equation is what happens when you reach equilibrium. When you reach equilibrium, what we find is that you can determine the value of an equilibrium constant directly from the standard potential of the cell.